Okay, my wonderful students, I'm glad to see you all here, and I want to wish everyone a happy Thanksgiving Day in a couple days, and hopefully you'll enjoy a day of Thanksgiving. I want to also just mention that I've had an enjoyable semester with you guys in here. And I've gotten to know some of you to one degree or another. Some of them I haven't, some of you I just know by sight. Some of you I've talked to, some of you I've messaged in web courses. But you know, the thing is, teaching is a lot of work, and if you want to do a good job of it, and but I just enjoy you guys. I enjoy students, and I enjoy the material. You know, I'm an egghead, and I enjoy students, so I consider it a privilege to be able to teach you guys, and I just want to tell you that you've done a good job this semester. Most of you have, anyways. I'm not looking at anybody, but anyways, I just want to say that. I try to say it. You know, you don't hear it enough. Who hears it enough that a word of encouragement? You know, especially from a instructor at UCF or whatnot. And so the Lord knows I haven't heard it enough, and I'm guessing that's true for just about everybody. We have a week planned ahead of us, just a week left, basically, after today. But before we go into the week's plan, I want to mention something to you that it actually grieves my heart to mention it, and that is, if you're using an iClicker for a friend, and your friend's not here in class, and you're using their iClicker for them, that is cheating, all right? And I don't want you to do it. And as soon as I decide to, I can check, and we can figure out who's doing it by various ways. And this morning, in my morning class, I confiscated a couple clickers from a student, from his friends and his iClicker. And it's going to be trouble for that student. Now, I don't want that to be the case in here. So just operate your iClicker. If you're not doing that, if you're operating somebody else's, that's no good. All right, we don't want any of that. Now, let's take a look at the week ahead. Today, we're going to talk about core collapse supernova, which is one of the two main kinds of supernova detonations. There's a picture of a... Does that look like a brain? You know, like somebody's brain MRI? But it's not. It's like a supernova simulation, false color image. Next week, Tuesday and Thursday, we're going to talk about black holes and the curvature of space-time, as I have promised to a few of you that we will do. We will hit that next, and we'll have a good session. And I guarantee you that what you learn will be unlike anything you read on the internet about black holes. And it'll be true, because that's what I want to do. I want to talk about stuff that's true. Also coming up on Thursday, last 20 minutes or so, we will have a mini review, kind of like the self-paced polling that we do at the second part of exams. I'll give you a handout with maybe 15 or 20 questions, and you'll operate your clickers and talk with your neighbors and just, study together. So like a little 20-minute review session with you and your neighbor. So sit with somebody that has a brain and that is friendly with you, and you can coordinate on that. And I'll take your scores in over the iClicker, just like in class, on exams. And then I'll convert your score into 3-4 bonus points. And this way, If you've lost out on getting to the observatory for bonus points, you'll be able to get a few this way, all right? Because you're supposed to be in class. So even though you cannot go to the observatory because of work, your job, your boss is a real, you know what, you can still do this, all right? Now, another thing that we will do next weekend is a big mega review homework. And that'll run from like Friday next week until the 7th, which is the exam date for the morning class. And who's got the syllabus up? This class, it's the 9th, I believe. Is that, can you? 5th? Okay, so we're the 5th. Okay, so you guys are, so it'll go till the 5th. Actually, it'll go to the 4th, midnight on the 4th. And then on the 5th, you have your exam. That'll be converted into bonus points, and you'll have like 4 or 5, 6 attempts to do it, and so you can study with your friends in a little study group, whatever you have going, and that'll help out. And so you'll be able to get a few, maybe 3 or 4 bonus points from that. All right, and then next Thursday, hopefully, there'll be a good observatory session, although it started raining today. Hopefully next Thursday it'll be nice. And if the weather cooperates, and if you write legibly, like I got I don't know who it's from. Because it was illegible. It was written in like a highlighter. And I'm like, how am I supposed to read a highlighter? It wasn't ink. It wasn't like a black Bic pen or anything like that. It was a highlighter. And I'm like, and it was messy handwriting. And so it's, that student's not going to get any points for that one. So when you go Thursday night, bring a good pen or a pencil. And if you have messy handwriting, make sure your name and the date is in there and things will go good. By the way, you may have noticed that I posted the 10 bonus points for the lunar observation session by the CFE Arena several weeks ago, and I finally got that in the books. And I alphabetized the November 1st session. That was a couple weeks ago. I believe that was a Wednesday or a Thursday night. And so what's today, the 21st? So Thursday's the 23rd. So yeah, 3 Wednesday nights ago. So I have that, it's all alphabetized, but I'll probably put those in the books tomorrow sometime, so if you're expecting that. And then if the November 30th session next Thursday is a go, if they are green, I'll put a slot in for that, and hopefully you guys can get over there and nab some bonus points. All right? Any questions about this plan for the next week? Yes, Ann? Oh, yeah, I am having office hours. Matter of fact, I'm having mega office hours. And you might want to jot this down because I'm expanding my office hours. Monday, 9:30 to noon. Room PS 156, that's my regular office in the Physical Sciences building, 9:30 to noon. Wednesday, regular, 9:30 to 11. In room PS 158. All right, it's one door, the other side of the elevator from my regular office. Next Friday, 9:30 to noon. Room PS 156. So slide in there if you want to double check your grades, or if you've got something smelly going on with your eye clicker or whatnot. And the Monday and the Friday will be individual office hours. So in other words, it'll be one person at a time because my office isn't big enough to hold a whole dozen people or anything like that, unfortunately. you ever notice that in like movies from Hollywood and stuff? Whenever they show a professor's office, it's like gigantic. You know, it's got wood paneling and sofas and a little fireplace. That's like fantasy land compared to the actual offices that we get. They give us, it's pathetic what they give us compared to Hollywood anyways. But so anyways, so mega office hours next week, Monday, Wednesday, and Friday. All right. Okay, I want to talk about, question up front.
I know I keep bugging you about this, and I'm sorry, but are you ever going to post those like blurb sheet things?
Oh yeah, blurb sheets. I got to do the blurb sheets. I've got so much stuff to do. And really, for a study, there's a study tool, and what I really need to do is just get them ready for the end of next week. So I'll try to do them when I'm not rendering thanks on Thursday, Friday, or Saturday. I'll try to do those. I know I got to get them done. By the way, on another note concerning grades and stuff, I put up best 2 out of 3 midterms for just about everybody. It's all squared away. So you can actually now estimate what your grade is going into the final. All right. And I normally do that. And I do that in office hours. Students come in, we'll take a look at your file, see what your grade is. And normally I don't add in bonus points, but you can do that if you've got some. I tend to leave the bonus points over to the side till the very end of the semester after the final, after everything's done. Then I round them all up and get them in there. Question in green. A bonus point counts as like a point on an exam that you do not drop. So, for instance, if you drop exam 3, I don't know which one is your best 2 out of 3, but let's say it's exam 3, okay? Those points disappear, but your other exam points stay. And every bonus point is like 1 point on the exams or the final, that you take. Question over here. Of course, you can office hours are your agenda. So whatever it is you need to talk about, you can double check, and definitely talking about concepts. What? No, she's not doing office hours.
Sorry, guys.
A normal person, if they knew what Courtney's schedule was, they would not ask that, because she's over here grading for another class while she's supposed to be TAing for me, and I overlook it because
You're a good person.
I want her to get 2 paychecks. But anyways, no, but I'll be there, so I'll be there, and we talk about, price of tomatoes in China, whatever you want to talk about. Our topic to start today is exotic fusion reactions, the trouble with iron. And that is really the kicker when you're talking about supernovas. When you're talking about a supernova, iron is the thing. Iron has got this special character, the isotopes of iron, and we're going to talk about that in the context of supernova. Now, this is a famous image from the Hubble Space Telescope. This is what we call a supernova remnant in the constellation Cassiopeia. And it was a supernova that we observed on Earth maybe 400 years ago or so, 1600s they think. They're not really sure, but they think it was sometime in the 1600s. And it's called Cassiopeia A, and we're actually going to have several images of it. And this is the visible light image from the Hubble Space Telescope. Now, to start with, I want to do a clicker question with you. So get your clickers ready. Oh, What was that, guys? Max, where are you at? Max. DD. Got it? All right. All right. And, yeah, so this is a stroll down memory lane, kind of a little review. See if your brain can read carefully. Make a decision. Can you maximize that? I have a feeling we're going to want to look at this one.
I can't move it.
You can move that thing. But it's good. It's good. This is good.
Yeah.
It's Windows. It's a Bill Gates system. Piece of junk. Did you know that his vintage late 70s MS-DOS is running in the guts of the Windows to this day? It's incredible. Yeah, question. Sophia. Dude, what does no base mean, you guys? What does it mean? Dude, you're out of order. That's incorrect. What does it mean? I keep using the word dude. D-U-D-E. No, not the refresh button. It means you're not on the right frequency. Yeah? And you're still getting? Bring it up here. Come down to the front. Bring your stuff. Just sit up here. Can you? No, just come up here and click from the front. All right, 30 seconds to get up here. Hey, click. This is embarrassing. Sorry, Sophia. This is not your day. All right. Is it still no bass? Maybe you're just too far away.
Can I put like DD? And then I say like, okay, so I put DD.
Go nitro. Ready?
Okay, and then I click play.
What's your? Don't say it out loud. Dude,
Okay, I swear it said no base. I did it twice.
sit in the front row.
I did it twice.
Okay, it must be a weak battery or
I
something.
did it twice.
How embarrassing! Gosh. Anyways, the mystery is solved.
I did
Yeah.
twice.
Yeah, it's all right. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, zip zap. Okay, yeah, the option here that's correct is B. And the majority, the majority, and even Sophia, anyways, there's a small decrease in the mass. So what that means is the E equals M, the M in MC squared comes from the mass of the 4 protons. So go ahead and make a sketch of this. Here's the 4 protons coming in. That's your input. This is the proton-proton chain, the PP chain. All right, so 4 protons in and a helium nucleus out. These 4 protons are fused together in that long process that you just saw. And these things over here, go ahead and circle those 4 protons, zip it in there. They are a little bit heavier. Not much. It doesn't take much. You get plenty of energy out of a little bit of a difference. So this job over here, another way to say it is, that helium-4 is a little bit lighter than the stuff that went in. All right, so some kilograms of mass got zapped. And according to Einstein's formula, it got zapped into E equals mc squared energy. And that's how the fusion reactions go. Now that whole idea that the output is lighter than the input, some mass goes missing, very small fraction. That is the key to understanding supernovas. Now, I want to get onto the topic in specifics. Go ahead and make a note, periodic table of the elements, and a couple things about, now you don't have to sketch in the entire periodic table, but maybe you could sketch in the first couple rows. Up at the top of the first row, hydrogen and helium. And we know, we've talked about it, they're the most abundant elements in the universe as a whole. Although here on the surface of Earth, this little neighborhood that we're in, no. But on the universe as a whole, yeah, it's roughly 3 to 1. And they make up 90-something%. It's like 1% for everything else. Now, if you're talking about the crust of the Earth, you want to see that one again? I'm going to burn these babies in there. All right, here it comes. Fire. Okay, so aluminum, silicon, and oxygen, and the order is oxygen is most abundant by weight, and you can make a note of this, 46% oxygen by weight. In the crust, now the core of the Earth we think is iron and nickel metal, liquid and solid metal. But the crust, which is right below the bedrock, 46% oxygen, 28% silicon by weight, and aluminum, 8% approximately. And so we're talking, that's 82% by weight. So that's 3 elements. All right, now that's the crust of the Earth. Now if you go down into the mantle, that's below the crust. That's where all the molten lava comes from. The proportions and the abundances are slightly different. And then the core, slightly different again. But for the crust, those are the specs. Now, a massive star is going to manufacture everything up to iron 26. So let me just scoop this around here. Everything on the periodic table up to number 26, iron. And it's the abundant iron 56 isotope that is where things stop in the core of a star. So you've got a small star, you've got a big star, they're all going to be cooking stuff, starting with hydrogen, converting it into helium. All right. And then eventually the helium, they'll start, they'll get, the helium will stack up in the middle and they'll start converting helium into carbon and other stuff. All right. And then it'll just keep going and work all the way up to iron. Now here's what the layers look. If a star is big enough, and this is from chapter 23.2, Evolution of Massive Stars and Explosive Finish. This is figure 1, and it's a good one. These cores, or these layers, give you, let me get my cursor. So here's iron. That's the last thing that fuses. That's a fusion product, iron 56 nuclei. And then outside of that, silicon and sulfur, and then oxygen, neon, carbon, helium, and then the outermost shell, fusion shell, depending on conditions, is going to be hydrogen. All right, now that's in a big star. Right? And we think that is the procedure in a big star. Now, the sun's not going to go through this. The sun's going to make a little bit of helium, and then it's going to maybe turn into a red giant and kind of fizzle out as a white dwarf. All right? But a bigger star, you'll start to get in these exotic. And matter of fact, let's look at a bigger star. The fusion reactions change because of the higher pressure. If you're a larger star, the core is going to be more compact, more dense, higher pressure, higher temperature. Now, in a bigger star, just maybe 50% larger than the SUN, you'll get something called a carbon, nitrogen, oxygen cycle, the CNO cycle. And it's making helium, but not like the proton-proton chain. You still have 4 protons out, and you still have a helium-4 nucleus. You have 4 protons in. 4 protons and a helium-4 nucleus out, but you don't make more carbon, nitrogen, and oxygen. You got to have some. They're like a catalyst, actually. It's like adding an enzyme or a catalyst to a reaction. Okay, the catalyst doesn't disappear; it just gets recycled in another round of the reaction chain. All right, so this one doesn't produce it, but eventually, after the helium in the core is exhausted, then you are going to start making carbon and stuff like that. So here's a pull quote from chapter 23.2. After the helium in its core is exhausted, the evolution of a massive star, so this is much larger than the mass of the sun, takes a significantly different course from that of lower mass stars. In a massive star, the weight of the outer layers is sufficient to force the carbon core to contract until it becomes hot enough to fuse carbon into oxygen, and then neon, and then magnesium. And that's how you start getting these layers. The hotter the temperature required, the deeper the layer. All right? And so it's, you start with CNO, then you start with a little bit of helium fusion, and then you start cooking up carbon and all the other exotic, I shouldn't call them exotic, all the heavier particles in the core of a star. And here's another pull quote. This cycle of contraction, heating, and the ignition of another nuclear fuel repeats itself many times. Now, this image, I want you to take a look at it. This is an image of Cassiopeia A. But it's in several different wavelengths of X-rays. And so this false color image over here shows the presence of iron nuclei, the red one. And this one in the middle, that shows the distribution in that, that big cloud of smithereens that we saw. Okay, this wavelength of X-ray, false color green, is connected to silicon and magnesium nuclei. All right, so that supernova blew itself up, and some of the silicon and magnesium layers are scattered here. The core got scattered like this. And then over here, radioactive titanium. Yeah, radioactive titanium. All right, so when we're looking at Cassiopeia A, we're trying to understand a lot of these exotic reactions. Now, here's some of the simpler ones. These are called helium capture. All right? The first one over here on the left, that's a carbon capturing a helium and fusing, and that makes the new nucleus a little bit lighter. That's oxygen 16. We got a lot of that in SMOW. 8 neutrons, 8 protons, and that's the output nucleus. All right, so a carbon-12 nucleus and then a helium. Yeah, those guys fuse together. You get energy. It takes energy. It's got to be going pretty fast. It's got to be hot. But when you fuse them, you get even more energy out than you started with. So that's going to heat things up even more. And my wonderful students, this extra energy output is how a star stabilizes itself against gravitational collapse. A star is a self-gravitating system. That means that it's big enough that it will form a sphere under the force of gravity. But if there's nothing to stop gravity, it'll keep contracting. All right? But these babies, these reactions will provide plenty of thermal pressure outwards from the core. Second reaction. All right, let's say one of my oxygen 16s, I just made one. Let's fuse that with a helium-4. What do you get? Well, you get a neon 20. 10 protons, 10 neutrons. That's a noble gas. All right? Now, these are nuclear reactions, so we're not really worrying about the electrons. They're just zipping around everywhere. What happens if you take a neon 20 and fuse it with another helium-4? Because there's a lot of helium-4 around. There's not much neon, not much carbon, not much oxygen, fairly small, but where you do find them, you're going to find a magnesium nucleus being manufactured. So these heavy nucleus factories in the core of a star, that's how all the elements above helium are made. All right? If you had Chick-fil-A for lunch, strips. Raise your hand if you had Chick-fil-A for lunch. One. I doubt that. Okay, who had Chick-fil-A for breakfast or lunch? What are all of you guys like? That can't be right. I see tons of people in there. Yeah, there's a lot of anyway, so Chick-fil-A, if you go in there and you get some strips, okay, that's bread, right? The breading is from the, and so that's carbohydrates, carbon, hydrogen, oxygen. Okay, so the carbon and the oxygen, right here. The meat, the chicken, it's got a lot of nitrogen in it. Okay, that's why it's protein. The N is made in a different cycle. Let's take a look at this. All right. So here's silicon. Oh, silicon. You mean the silicon in your computer? Yeah. It's made inside of a star, a big one. Billions of years ago, that already just like the McKeegan article. We found that little hot spot with a very, very hot oxygen isotope from a red star, at least 4.5 billion, 5 billion years ago. Same thing here, silicon in another hot star. That's a silicon, that's 28, isotope 28. That's a carbon 12 and an oxygen 16 fusing together. And yeah, you get energy out of this baby. Okay, so that'll keep the thermal pressure going. What about 2 oxygens? Yeah, no sweat. You get a sulfur nucleus, a sulfur 31, and that one is a little bit unstable. It ejects a neutron, a gray neutron down here. All right, so that neutron goes into the mix. So you got, inside of a star, you just got this big, maelstrom of particles. But these are some of the reactions that are cooking down there. All right, 2 silicons, 2 28s. Nice. That gives you iron 56. And that, my wonderful students, is finito. That's the last fusion reaction that you're going to get thermal pressure to support against inward gravity. Right? Now, all the other ones, you don't get bonus energy output. And I'll explain that in the next slide. This is the trouble with iron. Now, go ahead and make a note of this website, webelements.com. It's really nice. I like it a lot. It has a clickable tile for every element on the periodic table. So you just click on an element. You can read all about it. Its mass, the isotopes, how abundant it is in the earth, how abundant it is in the universe as a whole, water, and all kinds of stuff. So here's some of the tiles for aluminum and iron. And in the periodic table, The mass number down here for iron, it rounds up to 56. All right, so there's a lot of iron 56s, but that's not the only isotope there is. All right, so there's some other isotopes below 56. But what we're going to do is focus in on iron 56. So let's take a look at this. And what we're going to do is compute the weight per nucleon. In other words, a nucleon meaning something that's in the nucleus, either a neutron or a proton. So nucleon is a generic word that we would use. Kind of like at Chick-fil-A, you could use the word strips or nuggets to denote, whether it's a strip or a nugget, so kind of, or just say Chick-fil-A. All right, so the nucleon is a generic term. Now, the exact specs for aluminum 27 and iron 56 nuclei are right here. All right? And write down all those digits, my wonderful students. 26.981, 5386 for aluminum 27. Now, this is just for that isotope. All right? Aluminum's got a few isotopes as well. But for aluminum 27, this is its mass. Now, for iron 56, this is its mass. Write down all those digits. Now, don't worry about having to mesmerize that for the final. If I ask you questions about them on the final, they'll be in a table of some kind on the cover page. Or I'll put them verbatim in the question itself. Maybe a table. All right? Now, what we're going to do is divide this number here for aluminum by 27, because that's how many nucleons are in the aluminum 27 nucleus. And then this one over here, you can get your calculator out and do it. We're going to divide this one by 56, because that's how, this is the mass in atomic mass units of iron 56. All right? So we've measured all those isotopes. What they do is they do these experiments in atom smashers, like out in California or Chicago. They have a big one. Geneva over in France. They got them, Japan, they got them. Various places, Russia. Now, for aluminum 27, that quotient works out to 0.999316244. Go ahead and write down 9 digits. And then for iron 56, it works out to 0.998838202. All right, now write down those 9 digits. And now look at what we got here. The first 4 digits tell the tale. All right? Look at those first 4 digits in each one. Aluminum 27, 0.9993, 3 nines and a 3. Iron 56, slightly less per nucleon. All right? So that means iron 56 is a heavier nucleus, but on a proton for proton basis, neutron for neutron, it's a little bit lighter. 0.9988. So that's 2 9s and 2 8s. Right? Now it's a small difference, but it is significant. And for this reason, you can't break apart an iron nucleus with nuclear fission, the way we do with uranium, and get any equals mc squared extra. All right? You can do it. You can break these nuclei, but you won't get, you can break this one apart, you can split the nucleus, but you won't get excess energy. It takes more energy in than you get out, so it won't support a star. By the same token, you can fuse iron with something else. You can fuse iron with a helium nucleus, and the result will be heavier than the iron and the helium nucleus together. So you won't get any equals mc squared out of fusion either. Okay, so iron cannot fuse to a lighter, it can't fission to a lighter nucleus. And so therefore, for that reason, you don't get any excess E equals mc squared out. You know, the way that you do with proton chain, for instance. And all those other exotic reactions. We got a little bit of E equals mc squared missing mass for every reaction, but you can't with iron. So iron is where things stop in normal self-gravitating stars. You know, it'll just stop. And that is a problem. So here's another pull quote from chapter 23.2. Of all the nuclei known, iron is the most tightly bound, and thus the most stable. And this is why you cannot get more energy out of it than you put in. Now, hydrogen fusion, you fuse two protons together, you get more energy out than you put in. That's why that proton-proton chain supports the SUN against gravitational collapse. But iron, you got trouble. Because this is true when the core is completely dominated by iron, you get a supernova explosion. And this was the Crab Nebula. This is an image from your textbook. A few different actually, I think this one is in the, the introduction, section 1. Crab Nebula, this is a supernova remnant, just like Cassiopeia A is a supernova remnant. And so you get trouble. You have supernova detonations. Now, let's go over the supernova types. There's the Crab Nebula over to the side there. Type 1A is what we call a white dwarf supernova. If you have a white dwarf in a binary star system, it'll be possible for the white dwarf to start sucking stuff off the surface of its companion star. Now, our sun is going to eventually become a white dwarf, but right now we're not in a binary star system, so little chance for the SUN to become a type 1A supernova. But if its binary companion is close enough, it'll start accumulating mass from the nearby star. And once you get to a certain density, you'll get a thermonuclear detonation. In other words, you'll get a catastrophic runaway nuclear fusion reaction. It's like a hydrogen bomb, except it's many powers of 10 larger than anything that we could, the hydrogen bombs, the biggest one that the Russians or the Americans have is maybe a few kilograms of material that's fusing. We're not even close to that with this thing. This is many zillions of kilograms. Okay, we can see them halfway across the visible universe. And type 1A is what we would call a white dwarf supernova or a type 1A supernova. The other kinds are type 2, type 1b, and type 1c. Now, these the Roman numerals are a little bit shaky. They develop, it's kind of like the spectral class OBA, FGKM. It's not alphabetical order because they didn't really know what the true temperature color order was. If they did, then it would be A, B, C, D, E, F, G. But it's not. The same thing here. They originally thought that type 1A and type 1B were similar, but they're not really. Type 2, type 1B, and type 1C are the ones that are similar. And basically what we feel is that they're the iron core collapse from a large mass star. Now what happens, the iron core starts to collapse. And eventually all the protons get squished into neutrons, and it emits a wave of outgoing particles called neutrinos that modulate the transition from a proton to a neutron, and it's kind of a complicated nuclear reaction, but you get an iron core collapses. It's then supported against further collapse, and you get a bounce. All the matter above the core, it keeps dropping downward, collapsing inward, but then when it hits that neutron core that will not collapse further, it bounces and it creates a shock wave. And that outgoing shock wave is where all the other elements are created above iron 26, gold and silver, uranium, all those other heavy elements are up there above 26. They're created in these exotic shock wave induced nuclear reactions. All right, so the energy coming in is from the shock wave from the bounce. And so you have a ball of neutrons left. That is what we call a neutron star. So all this stuff, it bounces. They have this shock wave going outwards at enormous speed, converting all these particles into, like gold nuclei and silver nuclei and platinum nuclei and all that stuff. Iridium, all the elements on the periodic table above iron. And then you have this ball of neutrons left. And it's called a neutron star. And it has specific properties. It's considered an exotic astrophysical object. However, if that ball of neutrons is large enough, it will not support the supernova explosion. And what happens then is further collapse. A lot of neutron stars are stable. But if they're big enough, they'll keep collapsing and you'll form a black hole. An object that has mass but has no dimension. It's shrunk down to zero volume. Think about that. Question?
So how many neutron stars would you say are out there?
Oh, how many neutron stars are out there? Boy, I don't know. A lot. We see a lot of them. The ones that we can see are known as pulsars. And I'll tell you about that in just a few minutes. So here's this little mini spec sheet on type 2 supernova. Now, I'm going to show you some images. Here's a supernova remnant, we think, type 2 supernova. Here's a famous one, SN 1987. This is a type 2. All right? Now, let me get this movie. Now, I want you to watch this. We'll try to go through it at least once. Years are changing. 96, 97, 98, 99, 2000, 2001, 2003, 2005, 2006, 2007, 2008, and the last one, 2009. And did you see how it changes its look? It gets bright. The center starts out pretty bright, and then it dims out. And then the ring, and that's that shock wave. That's the shock wave proceeding outward from the collapse. All right? Let's take a look at it again. Here it comes, 94. Bright center, dimming out, dimming out. The ring is getting brighter. Oh my goodness. Look at that. Woo, baby. And you can see it's not perfectly symmetric. We're still trying to figure this out. We picked this up visually in the Roy G. Biv in 1987, and then as soon as you could, everybody turned every conceivable telescope, X-ray, ultraviolet, infrared, radio, Roy G. Biv to see this and measure this brightness. And we're still trying to analyze it. But that ring is where the shock wave induces a lot of exotic nuclear reactions above iron on the periodic table. Now, here's another picture. One's from the Hubble Space Telescope. That's what we were just looking at. And then this one over on the right is from the Chandra X-ray satellite that observes. So this is false color X-ray. And you can see that shock wave is ultra bright in X-rays. X-rays are very high energy, and therefore you know that there's a lot of nuclear reactions still going on there. Okay? Now, here's a couple specs on this supernova. We first saw it in 1987. That's why it's called Supernova SN 1987A, meaning the first one. And we can see supernova detonations halfway across the visible universe in way distant galaxies. But this one was fairly close. The location, our local group. It's in the Large Magellanic Cloud. Now, the Large Magellanic Cloud is a dwarf galaxy that's orbiting I don't know if it's orbiting us or Andromeda, but the Milky Way and Andromeda are orbiting each other. They're gravitational interaction. And then the Large Magellanic Cloud is a smaller galaxy, and it's interacting with us as well. And there's another one called Small Magellanic Cloud, okay? And it's also, this one was in the Large Magellanic Cloud. It was discovered by Magellan when he went into the South Pacific, 500 years ago, almost. We picked up a neutrino burst from this specific, with the Kamiokanda neutrino detector in Japan. It's directional. They know, they can pick up with this detector that's buried under a mountain about 3,300 feet under the earth. It's basically a big unit of purified water. And they know that these neutrinos, these little neutral particles that come out of nuclear reactions, they knew that a burst of them came from SN 1987A. The shock wave, we think, is at about 100,000 miles per hour. It's fast. It's not nearly the speed of light, but it's still pretty fast. Okay, here's kind of what we think the structure is. The stuff that's already, the shock wave is out here. The forward shock wave is out here. And then the shocked ejecta is this stuff out here that's producing a lot of light. And then the stuff that's already cooled off is on the inside. We think it was originally a blue supergiant, not a red giant, not a red supergiant. And this ring that we've been looking at is about 1.32 light years across. All right, it's getting bigger and bigger. All right. And just so you know, the Kamiokanda detector, we've got one out in South Dakota, a neutrino detector in an old gold mine out in the Black Hills, the Homestake gold mine. And down there they've got a big container of dry cleaner fluid that happens to be really good stuff for reacting with neutrinos as they zip by. Neutrinos are neutral particles. They'll go through like a light year of lead without interacting. But occasionally they will on their way through a light year of lead. One or two of them might. If you have enough neutrinos going through there, they'll interact with a lead nucleus. And so when you've got neutrinos breezing through you like you're not even there right now. Neutrinos from the sun. Neutrinos from anything will breeze through you like you're not even there because they're neutral, so they don't interact. The reason that light interacts with your skin is because it interacts with the electrons in all the atoms in your skin, in the molecules of your skin. But neutrinos don't do that. They just kind of zap right through. But you can observe them using dry cleaner fluid. So, they got thousands of gallons. The one in Japan is ultra pure water. They have a very, very fancy one up in an abandoned nickel mine up in Ontario, really deep. and it's filled with heavy water. And it was going for several years trying to observe neutrinos coming out of the SUN. There's another one in Italy, underneath the mountains that go up and down the spine of Italy, a place called Gran Sasso. And they have neutrino detectors. I think the Russians have one, and there's a few others around the world. And we're trying to use them like we used them for SN 1987A. Now, I want to talk for a minute or two before we dismiss. You guys feel like dismissing early today? Yeah. Hey, raise your hand if this is your last class before you take off for Thanksgiving. Sweet. All right, so let's talk about neutrino leftovers, supernova leftovers. All right, now neutron stars and white dwarfs are considered leftovers. And a neutron, a white dwarf is, an exhausted star. And it's usually the core. All the outer layers have been blown off. It's a planetary nebula of some kind. Usually we think that a white dwarf is going to be about the size of the Earth. Now down here you see the indication there's a little teeny blip down here. A neutron star. Well, let's blow that up. Let's blow that up so that we can see the neutron star as a sphere in the neighborhood of something about the same size. It's pretty small, right? Yeah, it would fit comfortably inside New York City or inside Orange County. So its distance scale is metropolitan, size of a city. Whereas a white dwarf is about the size of the Earth. So a neutron star, here's what a neutron star looks like, we think. About maybe 1.5 times the mass of the sun, 12 miles in diameter. Solid crust, and then we think kind of a liquidy core. In other words, slightly bound, and then a solid. Now, the interesting thing about neutron stars is, a neutron, a big ball of neutrons, what is it going to do? It might be kind of hot, but it's not going to really radiate much into space unless it has a magnetic field. If the original star that blew up in a supernova had a magnetic field, the magnetic field will be is kind of welded. It won't go away. It's all shrunk down and concentrated into the neutron star. Now, the nice thing about that is a strong magnetic field, just like the magnetic field of the Earth, we see the aurora borealis. A neutron star can emit very strong radio frequency radiation. And in 1967, a graduate student in England named Jocelyn Bell, she's now a professor. Go ahead and write that name down, Jocelyn Bell. She discovered the LGM, the first neutron star. Now, the way she figured it out, she was listening on a specific wavelength through a radio telescope, kind of like in that movie Contact. And she was analyzing the signal, and she noticed that the signal went up in strength and down in strength. And then it was quiet, and then it up in strength and back down. And so it was a pulse. Increase in intensity, decrease in intensity. Increase in intensity, decrease in intensity. Increase in intensity, decrease in intensity. Periodic basis, so she figured, oh man, what is this pulse? What is this regular, beep? I mean, if you listen to it through audio, it's going to be a beep. And just like they do in that movie Contact, they're constantly listening to stuff coming in through a radio telescope. So she said she was kind of wise. She kind of made she had a little fun with it. She said, well, what is this radio source? I'm going to call it the LGM. LGM. little green men. And she didn't think it was a little green man. She knew it was from some distant source. But, they called it LGM to indicate that this is, like, oh man, this is almost like somebody's trying to signal us. Except somebody trying to signal us wouldn't use a constant beep, 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 beep. They wouldn't do that. They'd be broadcasting, kind of like the internet, ones and zeros, you decode it and you get a coupon for pizza, And so that's so extraterrestrial intelligence would be, a series of beeps. But this is what we think it is. A neutron star, and the magnetic field, we say it's frozen into the neutron star. And if it's really strong, and if the neutron star is rotating, this part, the magnetic axis, if that is aimed at Earth, you're going to get a blast of radio frequency radiation. That's your beep. But if it's spinning like a lighthouse, just like a lighthouse, the light at the lighthouse is always on. It's just not pointing at you. So you see it blink. It's not blinking. It appears to blink because it's rotating. The same thing here with a neutron star. So Jocelyn Bell discovered this lighthouse effect in a neutron star. She figured it out, and this was the first pulsar back in 50 years ago. And she was a grad student. She bagged it. She figured it out, right? But because it was England, the guy that got the Nobel Prize for this was her thesis advisor. And some other cat. So he's over there going, I say, old chap, and all that kind of stuff. And she's in the lab analyzing all the data. She finds it. She figures out what it is, and he gets the Nobel Prize. So nobody talks about him. We only talk about Jocelyn Bell. So we want to make her more famous than him. So I hope you'll take that to heart. Now, neutron star. As I mentioned, a neutron star, what we call neutron degeneracy pressure, will support a star against further collapse unless there's too much mass, and then it will collapse on itself. And as we say, the mass of a star is its DNA. If the mass is large enough, you'll form a black hole. And this image that you see every day to start class is an artist's conception of what a black hole would look like near a giant star, a blue giant. So we'll talk about that on Tuesday next week. Have a great weekend. If you have a question about your iClicker, anything, come on up to the front.
Thank you very much.
You are welcome, Max. Good. See you next week. Right.